We are going to analyze now the last effect that will help us determine strength in acidity, and that is orbital. Referring to the orbital in this species, the conjugate acid, where the negative charge, the conjugate base, the negative charge resides. So that atom, where is that charge? In what type of orbital? And for that, we're going to analyze the following series. Let's say that I have this molecule, and this time I'm drawing the hydrogens. Normally, we don't draw the hydrogens, remember, attached to carbon. But I'm going to draw it this time. So that's acetylene. And I'm going to draw an alkene. And this time, again, because we're explaining acid base, I'm drawing the hydrogens. And here I'm not. This we know CH3, CH2, CH2, CH3. I'm just drawing one of the hydrogens here, one of the CH3. And we're going to be comparing this series. So next step, what I'm going to do is remove one hydrogen and form a conjugate base. So this is what I'm doing, taking one hydrogen out. This is the conjugate base, negatively charged. Then I'm going to take one of these out. I'm going to remove that. And this is my conjugate base. And last, I'm going to remove, this is my alkane. So removing that atom, there is going to form the following anion. That's my conjugate base. So I need to analyze those. And I know that the more stable this is, the stronger the acid here. So now, because we, in all those molecules, notice that the hybridization has changed. Here, the atoms are sp hybridized. So I have a carbon sp. Here, the atoms, the two carbon atoms are sp2 hybridized. And here, every carbon here is sp3 hybridized. Now, remember that when we form hybrid orbitals, for the sp orbital, we're mixing one s-type orbital and one p, meaning that 1 out of 2 orbital is s, and 1 out of 2 of the hybrid orbital is p. That is 50% s character and 50% p character. Now, when I form the hybrids here, I am mixing one s-type orbital with 2 p's, meaning that 1 out of 3 orbital is s. That's 33% about. And 2 out of 3 are p orbitals, about 66%. And when I do the hybrid orbitals here, I am mixing 1 s and 3 p's. That is 1 out of 4 is an s. That's 25% is character. And 3 out of 4 is p, out of 4 orbitals. So that's 75% character. If we remember, what is the symmetry of these orbitals? S-type orbitals are like that. P-like orbitals, P-type are like that. So electron density in the s-type orbitals, say for example in this period is the 2s and the 2p. So this is closer to the nucleus and this is farther away. So the more s character, the closer is that density to the nucleus. So here I have more s character. Notice here this is 50% opposed to 33 and 25. So this orbital is actually shorter and closer to the nucleus. Because the nucleus has positive charge, this anion is more stable. Again, because that electron density is closer to the nucleus than it is in any of the other. So the order, say, I'm going to rank those in stability. So the closer to the nucleus is the negative charge, the more stable the anion will be. So this anion is more stable than this, and this is more stable than the other. And The more stable the conjugate base, the stronger the acid. So now I'm gonna rank those in acidity using that explanation. So, and we did it, and I didn't say it at the beginning, but why are we choosing here specifically to talk about the orbital effect? Well, it turns out that here the atom reside, the charge where the it always reside on a carbon everywhere, so that doesn't explain, same thing. There is no resonance effect, so we check that and cannot explain the difference in acidity. They're not inductive effects, so none of that explains. Now that's why I analyze the orbital, and I see that this has higher S characters, so closer charge, negative charge, closer to nucleus is more stable. So now I am predicting acidities, and then according to that, the more stable the conjugate base, the stronger the acid. So this acid is a stronger acid as the alkene. So alkynes stronger than alkene, and that's stronger than an alkane because of that. So in checking that with our pKa chart, well, the pKa of acetylene, for example, is 25. The pKa, I'm going to draw it below, the pKa of here is 44, and the pKa of an alkane in general is 50. Notice it's much larger pKa, so much weaker acid. So in this series, the smaller number here is this, and the smaller the pKa, the stronger the acid. And this is what we had predicted based on the stability of the anion. So the more stable this is, the stronger the acid. And this is my more stable conjugate base.